Now more than ever, you need technology you can rely on.
頼れる人ですよね。
I'm a Dell Technologies advisor.
Ich auch.
我也是。
我aussi.
And if you're a small business, we're with you.
We are with you.
Estamos com você.
We want to help.
So we'll be right here.
At home, answering your calls, providing support,
And standing by you every step of the way.
Bye-bye.
Now, let me introduce you to Lalit Gajre, who is actually going to lead us to the next session. So let me give a brief intro to Lalit. Lalit is the founder and CEO of Vaston Inc. Lalit has substantial experience in HPC software development, cloud computing, machine learning, data engineering, electronic design automation. His past employers were Cadence, Siemens, and Synopsys. Lalit has a wealth of experience in license negotiations, technical project management with government agencies such as DARPA, DOE, and Gas Research Institute. And Lalit is also a partner in crime with me. We both track chair and chair AI ML track. And you'll see us both in TiEcon 2020, and also he manages the boot camp at TiEcon 2020. So with that, Lalit, I'm going to pass the baton to you. Thank you.
Minnie, thanks for the introduction. I really enjoyed Eric's presentation. It was really, really eye-opening. So let me go ahead and first of all, good morning, good afternoon, and good evening based on your location. I know we have a global audience. It is a privilege to open up the panel titled Hardware Enabling AI Revolution. This session will focus on hardware that is enabling the AI revolution. We have a great panel today who will cover a variety of AI chip hardware technologies right from existing GPU, FPGA to newer neuromorphic chips. Let me introduce you Chris Rowen, who will be the moderator for our panel today. Chris is currently CEO of BabbleLabs. In his prior roles, he was founder of MIPS, Tensilica, which was part of Cadence. And Chris is, he's very knowledgeable in the hardware space. So Chris, go ahead.
Thank you. So it's a great pleasure and honor to be able to lead this panel about hardware and AI. And just to kind of frame the question, I think it's useful to understand how AI and especially neural network deep learning really emerged 4 or 5 years ago. Not just as a new application, but really as a new computing model. Perhaps as fundamental as programming of ubiquitous microprocessors with high-level languages, which emerged 40 years ago as a transformation of the information technology universe. This may be the biggest thing since the emergence of the internet or the emergence of the ubiquitous microprocessor programming. And it really is particularly important because it has unique computing density, computing complexity, has unique memory requirements, and all of this is inspiring a new generation of silicon innovation. New silicon architectures, new silicon startups, new silicon methods are being driven by AI and deep learning in a way that is unique and which is something we haven't seen in a couple of decades in the silicon industry. So it's a great pleasure to have this industry brain trust here to participate. And I will quickly give you a profile of each one, and then we'll jump into some questions. We've met as a group and we've kicked around some slightly controversial questions, but I think there's also an opportunity for people to submit questions by chat. And we'll see if we can take some of those questions from the audience if we can fit them in. So we really want to take advantage of this opportunity to have this group of people here. Gaurav Singh is the corporate VP of Xilinx, responsible for silicon architecture, verification, system platforms, and embedded systems. He's been in the semiconductor industry for more than 20 years. His past work includes some significant innovation in the processor space at AMD with K6 and Opteron. So he really understands processors and the configurable computing platforms that Xilinx is so known for. Michael Kagan is CTO of Nvidia. He was co-founder of Mellanox, a decade as CTO, and before that, a decade as VP of architecture. Manoj Gujral is Senior VP and GM of SiFive. He has his focus on the silicon business, and he has a long history across the semiconductor industry at Nvidia, at Cavium, at Cypress, working on business and computer architecture. And Gordon Wilson is CEO and co-founder of Rain Neuromorphics, a 3-year-old startup focused on building brain-inspired hardware to enable a new generation of AI applications. So I welcome you to this, and we ought to jump into it. I think that one of the things that's most striking about AI and deep learning is the fact that it's applicable across a very wide class of different kinds of data streams and data content. It's vision, it's audio, it's motion, it's credit card transactions, it's sales figures, it's many different kinds of information. So as a computer architect, how do you look at this diversity? How do you decide, well, what's going to be optimal for a specific domain if you're really focused on solving just that use case? Or how do you build an architecture which successfully spans the diverse range of things if you want a more general purpose, more one-size-fits-all architecture that works across many different data types? So how do you deal with the diversity of requirements across the application space? Somebody want to?
Chris, I'm happy to jump in.
Go ahead, Gordon.
Sure. Go ahead, Gordon. Yeah. Well, first of all, Chris, I'm super excited to be here and kind of share kind of a more frontier perspective on hardware and the vision of how this next generation of hardware will enable future AI applications. But your question really points to something that I think is really necessary for all listeners to know. And the reason why we've seen such incredible success from Nvidia, from your company, is because, and as a general processor to support all of these new developments in artificial intelligence, is really because the GPU worked extraordinarily well as a parallel processor married with, I think, like this miracle of backpropagation, right? Backpropagation as an algorithm to learn information and to learn the patterns across many types of information, married to a very suitable parallel digital processor. This has been the backbone of the last 8 years of progress in artificial neural networks. Everything from CNNs for vision to reinforcement learning for AlphaGo to transformers and natural language processing, like we've seen with GPT-3, has been built on GPU parallel processors. So when we think about this at Rain, we're trying to think past von Neumann. We're trying to think past digital processors and ask, what is kind of still a universal or general architecture that we can build that is non-von Neumann, but can have the breadth and span for data types that NVIDIA GPUs have. And so for us, we really look at the brain for that inspiration, because the human brain has already demonstrated to be able to solve all these problems itself. So when we think about this, I think we want neural networks to be massively scaled up. We want them to be sparse. In our case, we seek to make them analog. But I believe that there is a next generation set of architectures that will be just as general as GPUs, but multiple orders of magnitude more efficient. So we can take the intelligence that's currently limited to data centers and put them into autonomous devices.
Great.
Yeah. And I agree with Gordon, Chris. Yeah, so I think that's definitely, you know, it's a, and by the way, just an honor to be here firstly at TI, but also with this distinguished panel. It's certainly a very interesting topic. And to maybe just to focus on the gist of your question is really that there is so much diversity in this field. It is evolving, and there's so many different applications that can benefit with AI and machine learning, right? It is intended to be ubiquitous, right? Just about any type of application can make use of it. So Gordon is exactly right that we need to focus on efficiency, and we need to think in terms of are there new paradigms, right, where we can actually bring much greater efficiency. The thing is that as we look towards a different variety of applications, I think we have to think in terms of, okay, what is needed for training versus what is needed for inference. And certainly, I think NVIDIA has done an extremely great job of really, focusing on, really big machines for training, because in training, you're really looking at, weeks or months of converging a neural network. And the folks who are actually using that are the scientists who are actually building the networks. But there's a separate area of actually applying these neural networks in more of real-world application scenarios, right? And in that space, really what is needed is that you need to accelerate the whole application, of which machine learning is a component. Inference in of itself is not the end application, right? Inference is usually a portion of a larger application. So what we really have to think about is how do we accelerate that entire application with focus on neural networks and focus on AI and machine learning rather than machine learning as in inference in of itself, right? So if that guides the thinking, then you really think in terms of, okay, what is the hardware platform that can not only accelerate the AI and machine learning, but also focus on accelerating the entire application, right? It's the whole application acceleration.
So this is Manoj. First of all, truly a pleasure and an honor to be here, part of TiEcon, and as well as part of this distinguished panel. A big part of my career has been, on the system side, and then also, Silicon being part of that whole platform. And, more lately, it's been all about AI applications. And Chris, all the applications that we talked about, eventually they're going to be consumed by some kind of a connected device, mostly a mobile device. So I think inference in a mobile device, some of the key attributes that are needed are reliability, latency, and power efficiency. I mean, I cannot emphasize power efficiency any more than all of us are aware of. But the key challenges of AI workloads for mobile applications is really that the nature of some of the AI models, it's very compute intensive. I mean, these are large, complicated neural network models which require complex concurrencies, and then the always on and the real time nature of the mobile devices. So I think the hardware architectures that we need to define, that we need to optimize, they need to make sure that they work in a constrained environment, and really thermal efficiency becomes an even bigger factor, largely because some of these devices need to have a sleek design. They need to have a decent battery life, as well as deal with the limitations of storage and memory bandwidth in these handheld devices. So I think to really re-emphasize power and thermal efficiency is really the critical to the promise of AI, especially on a broad range of connected devices.
Great. Michael?
Yeah. So, yeah, first of all, it's also my pleasure and honor to be here. And, my new capacity as CTO of NVIDIA, it's a very interesting opportunity for me to basically fuse together the networking technologies that we have developed at Mellanox and basically this best vector processors that are done on NVIDIA. And for me, it's in a sense, it's a little bit closing a circle, because before Mellanox, I worked for Intel, and my first design was the 860 CPU, which is the best vector processors about 40 years ago. So sort of, closing the circle now to the AI and neural networks and machine learning. As Gordon mentioned, it's a very, very new field. And I don't think we have a very clear understanding of what and how these things are working. And if you look at the networks that are developed today for the migration BERT is about 300 times more complex than RN50, and it is not. It didn't take too long to evolve from RN50 to BERT. So that's why both scalability and flexibility is really important when we're dealing with this. And you have to have this solution designed in a way that inference and training are not necessarily two clearly distinct things. It's like Gordon mentioned, human brain. Human brain does both inference and training at a time. So, and I think we need to think about these neural networks and these models in a similar way. And going to the gory details of people and development and so on and so forth. This panel is about hardware for AI, and most of us here are doing the silicon devices, but silicon devices without software is pretty much expensive sand, and not more than that. So it's really important to have the right frameworks and an environment for people to innovate and develop. And it is the great advantage, and actually I would say it's pretty much ultimate goal, to have this environments to scale from the very large and very powerful machines in the data center that are used to train huge networks, all the way down to the embedded edge and whatever small things that are doing inference and a little bit of training. So I'm with Nvidia for a little bit more than 2 months, 3 months. And well, before that, we actually worked with Nvidia at Mellanox for quite a lot. And there's a lot of challenges with the scalability, both scale out and scale up. And so this is I think the Nvidia, they've developed this framework and environment that people can both develop and deploy neural networks. Pretty exciting.
Yeah, let me ask a follow-up question. What specifically do you think is most different in the hardware requirements between inference and training? What are the things that will most distinguish architectures optimized heavily for one or optimized heavily for the other?
Oh, okay. First of all, I think it's not. I would not optimize heavily to either one of them right now. I think we need to support both. Now, in terms of the difference between training and inference, training inherently requires much more compute power, and on the inference you can get along with actually much smaller networks. You can prune your network for inference, and you don't need you don't necessarily need the precision that you do need on the training. The float 16 is pretty much the bottom of the precision for training, and sometimes you need 32 bits. On inference, you can get along with 8 bits, integer and 8-bit. So if you look at and that's one thing. There's less computing. You don't need to deal with the backpropagation, and it also has much lower pressure on the memory size and the bandwidth. So these are the sort of low-level things about the hardware details about, in my mind, between the inference and training.
Yeah, this question of memory is a really important one, because by and large, memory is what makes systems expensive. Memory bandwidth is expensive. Memory capacity is expensive. What does the rest of the panel see in patterns of evolution of memory systems for AI? What are some of the key things that we need to consider if we're going to keep pushing the envelope on efficiency and throughput of deep learning platforms, particularly around the expensive, power-hungry memory issues?
No, that's a great point, Chris. So I think in some ways, I think all of us know, right, the ones who've architected multiple different types of devices, right? At the core of it, the AI and machine learning requirements, right, are not that sophisticated, right? It's about a lot of compute, and I think you pointed out to a good thing, which is really memory. It's both memory bandwidth and how close can that memory be to that compute, right? Because the intermediate data that these networks generate either while training or with inference are fairly large, right? There's a lot of activations. Obviously, that's the data that you're pushing through. But then there's lots of intermediate data like weights, right, that have to be stored, right, and have to be referenced very quickly. So really the challenge is how do you optimize across the whole system? So what you really need is, in terms of memory, is you need a memory hierarchy that is customizable. The requirements that you need for, say, speech processing, say, let's say that's an LSTM network, are slightly different from what you would need for, say, image processing, right? What you need for, say, voice translation with a large network such as BERT, the requirements are slightly different, right? So you bring up a good point in terms of how do you bring memory close to compute, and I think what Michael said is relevant, right? When you think in terms of larger systems, you cannot quite put the entire network into one device, right? So now you need to start thinking in terms of how do you scale it out, and I think that's where the interconnect fabric starts to, play a big part, right? But in my mind, what you really need is a flexible topology where you can customize the ratio of compute and memory storage all in one platform, right? That's the ideal goal, right? And then you can have the same platform that can, really target the needs of a multitude of different applications.
Yeah, I'd like to add on top of this. This is, I think, a really interesting question about memory access, because I think it's one of the universal statements that we keep hearing about what we need for better AI hardware. We need to shorten the von Neumann bottleneck. We need to have better access to memory. And we see all these new architectures that are being primarily built for data center training applications and inference as well, but that are breaking memory into a lot of more pieces and trying to increase that parallel access to memory. But if I'm looking kind of a little bit further down the line, my thought is we need to combine memory and processing. We need to do processing in memory. There are a lot of companies that are already commercializing technologies like this for simple inference. Companies like Mythic that are doing flash arrays for simple inference, or Sentient. But when I think even further, we want to have the reason why, one of the fundamental reasons why we have such a massive compute requirement and all this time is because we're constantly moving data back and forth from our processor to our memory for these massive, high dimensional matrix multiplications that have, thousands, tens, hundreds, millions of individual calculations. So if we can move to architectures that combine memory and processing, like say with the Memristor, which I think is extremely promising over the next 10 years, then we could dramatically, we could eliminate the von Neumann bottleneck in theory, and really save a huge amount of time and energy in the process. And just one note I want to say about inference versus training. I'm so glad that Michael, you said you were talking about combining them together, because I think that right now we're shifting and we see a lot of companies that are trying to split them up. Folks that are trying to just move simple inference to the edge. And I think that is the first step, to take known intelligence and push it to the edge so we can, talk to our oven, or have our doorbell recognize our face, or something like that. But in the long term, I think we need to have devices that combine training and inference so they can adaptively learn as well.
Let me add another kind of perspective to that. I think at the heart of it, everything that that Gaurav and other folks talked about. At the heart of it, really, we are still using the von Neumann architecture. That's been around for 50+ years. So in this new and brave AI world, of course, large memory bandwidth, large memory size, a lot of compute power, we need to really fundamentally think about new computer architectures from ground up. And then, there have been a lot of vectors over there. Definitely, the processing in memory is one of the ones, that's picking up a lot of momentum. Of course, there's no mature silicon yet that implements that. But the end of it, once we address the memory issue, I think it will, from an architectural point of view, it will fundamentally address the whole power issue also, right? Human brain takes what 25 watts to really process all the stuff, both training and inference. And I think with best of the breed out there, we're talking about, kilowatts and megawatts. So we are still an order of a magnitude, away from where we want to be. and these fundamental, architectural schemes will address not just the memory limitation, but also the compute limitation that go with it, and the power, reduction that we really need to achieve to get to the point where we can process large amount of data fairly quickly and be very, power efficient.
Yeah, great. So on this panel, we have two big silicon companies making big bets on AI, and two smaller silicon companies making big bets on AI. And this conference is very much about innovation. And I'm sure the audience is full of people who are dreaming of, well, what could I do to innovate? So what are the pitfalls? What are the barriers? What are the things that make it hard and distinctly hard or distinctly easy about doing a deep learning silicon startup today, relative to other kinds of startups, relative to other times in history for doing startups? What's the good news for potential innovators in silicon? What's the bad news for potential innovators in silicon?
Well, I think good news for potential innovators in silicon is that it's a lot of fun.
Yes, absolutely.
Whatever you are doing, you just need to make sure that you have a fun of doing what you are doing. Now, and as I mentioned before, I think the biggest challenge for this solution is not just silicon, but the software and all the ecosystem around it. I mentioned that 860 CPU that I worked on, it actually didn't take off because Intel didn't manage to pull together right software to take advantage of this machine, although it was about 50 times faster than 486 CPU that was introduced about the same time. So the software and the ability to deliver the goodies of the hardware to the interfaces that people can consume and innovate them on, and actually open the scope and the range of people, of developers that can utilize them. That's the biggest thing that you need to take care in order to succeed.
I'm happy to
from
take
a
this
business
one.
perspective, yeah, let me just add a quick comment. The good news to add to what you just said is really that there's a huge market opportunity out there. Mm-hmm. I think we are not even in the first inning yet of this, of this baseball game, if you want to put that analogy. Tremendous amount of opportunity, and that's why you really see a lot of innovation, a lot of new startups. The bad news is, it's gonna take a lot of money. I mean, that's really the big thing, right? I mean, doing silicon in 7 nanometer or 5 nanometer, we are not talking about millions, and we're not even talking about tens of millions. I mean, now we're talking about hundreds of millions. So, which means, it's a long game. It's going to require a lot of money, which means, you have a lot of capital that's needed to really get to that point. And really eventually an integration of, hardware, software, and system to really deliver on the solution. So, which means you have to kind of innovate beyond just really the silicon, beyond just the hardware architecture. You really have to take an overall whole system level approach to really get to the endpoint.
Yeah. Go ahead, Chris.
Go ahead, Gordon. Go ahead.
Sure. All right. Yeah, no, I can definitely have a lot of war stories to share about, being an kind of upstart founder in Silicon Valley with a wild idea. But, I would say, for folks, if they're building an AI hardware startup today and their technology relies on Moore's law scaling, i.e. relies on being built in the smallest geometries in order to be competitive, then it's going to be very difficult, because just the sheer cost of tape out, even for like a shared shuttle, I'm not sure if you have shared shuttles at, 12 nanometer or smaller, but, the sheer cost of that is so vast, and the cost of an error is really, really high. So, in our case, we're not relying on Moore's law scaling. We're trying to build something that's with analog components and kind of scales in a different way. So we have the advantage of our first tape out being at 180 nanometer. But, I would say, the whole ecosystem has really changed, recently to be a lot more friendly to semiconductor startups. And I think, of course, the biggest limitation is access to capital. And one thing that I can say, having now been in Silicon Valley for 2 years and have been floating around Sand Hill Road, just over the last 2 years, the amount of knowledge that I think that VCs have gained and grown into, understanding the nuances of semiconductor companies, the milestones related to semiconductor companies, it has really improved. And you have, a lot of other types of things kind of growing into this new semiconductor ecosystem that make it a lot more friendly, from, incubators dedicated directly to silicon or exclusively for silicon, as well as, other types of benefits there. But yeah, it's not easy, but I think it is definitely fun.
Yeah, to add to that, and again, right, I think the advice that I would give is that understand the market and understand the applications. And what you might find is that you don't necessarily need a new piece of silicon, right? And if you end up needing a new piece of silicon, so be it, right? But there's a lot of innovation to be had at the system level, and specifically around the application. And to quickly point out, the inference versus training thing, right? Really, it is the optimization point, right? Even at the edge, you do need training, right? But you would optimize it more for inference rather than training. You want to do incremental training, whereas the high-end silicon and systems that are needed in the data center would probably optimize a lot more for the training piece, right? So pick the market. The good news is that there's this huge opportunity, like Manoj mentioned. But then do your homework and do silicon as a last resort, right? I think it's a huge challenge, right? And unless you actually have something that's truly differentiating, like what David has, right? So I think, like what Gordon has, right? Which is really thinking in a new paradigm, right? If you do have something where you feel you can bring that value, absolutely do silicon, right? But if you count the number of silicon startups that are out there, right, there may not be as much differentiation between them, right? So not all of them will survive.
Great. I want to ask one more question and then hopefully turn to questions from the audience. And the question is, what's ultimately possible? How far can we go in terms of throughput on a single model, in terms of operations per watt in evaluation of models, in terms of how general purpose things can be? How far can we go in coming up with architectures that really enable fundamentally new classes of applications? How close can we get to infinite computing without a battery, without any power at all? So what are the theoretical limits? What are the practical limits of what we might be able to do in the next 5+ years?
Well, within the next 5+ years, I think we can know what can be done. Basically, we all work with the foundries, and we all know what's there's their roadmap for 5 years. But looking forward, I'm optimist. I think the limits are limits by basic physics, like speed of light and stuff like that. So I don't think there is we should look at the limits. Let's assume that we can do whatever we want. It's just a matter of persistence and faith, and make sure that we utilize the available technology the best way we can.
Yeah, so I think that was a profound question, Chris, in terms of, could we do, infinite compute with zero power, right? I wish we could get there, and maybe there is some technology that can get us close to it. But I still think that, the power efficiency is absolutely important, right, in certain segments of the market. I think, Manoj mentioned the mobile, right, and there's the edge. But really, I think what we have to start thinking about is how do we optimize the entire application, right? I think, we can optimize and make the AI machine learning piece of it really, really efficient. But in the end, what really matters to the user is the entire application, right? How do you optimize the entire application? So it's still about all of the different data paths, all of the different, and what the interesting thing there is that there is no one solution, right, that can fit all of it, right? If you're doing edge around video, or if you're doing it around speech, right? Or if it's like a mobile endpoint, right? The application characteristics are actually quite different, right? And that's really where the excitement is, right? That, how do you optimize the entire application with machine learning as the key component to it.
Yeah, I think it's even more than the application. What we are looking for is to deliver the services, and services is sort of a chaining of very collaborative applications.
Yep.
And if you think about that, the data center is a computer, or this large large entity is a computer, is basically taking multiple applications. Each one can be different topology of neural network, or model of this sort, and they basically chain them together to deliver the services. And the compiler will be not taking the C code and compile it to the some binaries or some object code or assembly code. It's going to be a composition of these applications, chaining them together to deliver the service. And I completely agree with Gaurav that we need to optimize here at the service level, not on the individual application level.
Let me turn to some questions from the audience, and I'll paraphrase these questions. Are we going to see more diversity in the kinds of computing platforms, or more convergence? And I'm thinking about the fact that today we have ASIC-based implementations and CPUs and GPUs and TPUs and FPGA-derived approaches, and these analog methods. So we have a pretty broad span. Are we going to see a greater span, or some consensus building about what are the best class of architectures for deep learning? Yeah,
I'm happy to take this, Chris. Sure. Thanks. So yeah, I think that immediately, like in the proximal future, we will see this expansion of many different types of architectures that'll be proven and demonstrated. Whether it's optical or analog based with like flash or novel, memristor type technologies, or digital signal processing, FPGAs. And I think the reason for that is because these markets are so nascent. Like we have not yet been able to see what really is the right architecture or the best architecture for every type of like form factor and requirement, be that scale, flexibility, or efficiency. But I think that after a few years, like after we see enough of these new architectures kind of get a year or two to be played out, there will be kind of a great calling back, and we'll start to see one or two primary architectures start to dominate. In particular, like when we look further into the future and we, I think, recombine and start putting more training into edge devices, we'll start to see that things will begin to converge. But I think we're seeing an expansion now, and then there'll be a contraction in 3 to 5 years.
Mm-hmm. Other thoughts?
Yeah, no, I think I would definitely say, I think we're still at the early stages, and I think there will be this expansion, and I think people are coming up with new ideas, and I think there will definitely be an expansion. I think the other way to think about it is that if there is no single architecture that can fit all of the different requirements, right? And Michael brought up a good point about services, right? If you think inside the entire stack, then the thing to think about is that, you need an adaptable platform where you could bring your own architecture, right? Bring your own architecture and optimize a specific architecture and optimize it for the actual applications and services, right? So, there's one segment that will go there, right? But then there will be a high volume segment where, the market itself is going to speak and actually ask for a very specialized piece of silicon, right? So I think you'll see a combination of all of these, where in certain places, the market can actually sustain very specific solutions, whereas in the other end, you will need some sort of an adaptable platform where you can actually bring your own architecture, and you can bring your own memory hierarchy, you can bring your own application to be accelerated.
Yeah. Great. Here's another question. Oh, go ahead, please. Go ahead, Manoj.
No, I was just going to add to that, over the short term, like, Gaurav mentioned, definitely there's going to be divergence, but, I also feel, the field is so broad, and people are trying to optimize their solutions for certain applications, whether it's, for voice or video or vision and things like that. So fast forward a few years, you could also see potentially, an application-based architecture, something that's optimized for, voice, or optimized for, vision and things like that. I don't think there's going to be a one size that fits all, even in the longer run, 3 to 4 years from now. And given the amount of innovation out there, I do, at least, expect there are going to be, optimized solutions for each area of the AI application, and that's really going to drive eventual solution in those spaces.
Mm-hmm. Right. Good. So one of the questions, one more question that's come up. How long before we will have AI designing their own hardware chips?
Oh, we already have it.
Yeah, it's already happening.
Yeah,
right.
It's already there. Yeah.
So, say more. What are the best ways to think about AI in the silicon design flow?
Well, there's a multiple places where you can, where you can take advantage of AI, and actually it's being done today in the different levels and different companies, basically figuring out how to optimize various things. But taking it in the broader perspective, what we see, in the last decades, is that people are working more and more on higher abstract level. There used to be people, in the silicon design. I remember those that was, pushing polygons, and then translating RTL to schematics, and so on and so forth. Now nobody does it, right? And RTL becomes not a high-level language, but sort of a very low-level stuff where you want to compile your higher-level models to. So the same here. Okay, at some point you take your experience and knowledge of your silicon designers and or other hardware designers, and feed some model with the data that you can collect here and there, and basically doing this AI-based optimizations for different things, be it routing, be it timing consideration on the silicon and so on, or be it optimization of the system operation, like it's done in the data centers.
Yeah, I think we're already using that at Xilinx. We are increasingly putting AI into our flows, into the silicon flows. What machine learning can really do is figure out broad patterns, right? That it's not easy for a human to pick up, right? So, and we generate a lot of data as part of the silicon design process. So specifically in my group, for example, right, on the verification side and on the implementation side, right, we are actually using that data and feeding it into a network, and the network gives us a lot of visibility that we would not otherwise have.
Great. So I think we are. Lalit, I think we're coming to the end of our time. Is that right?
Oh, we have 10 more minutes.
Oh, we do. Okay, very good. So I have another question that is sort of what happens when you get a group of really experienced industry experts. You ask them to predict the unpredictable. So what's the black swan event? What is it that could fundamentally change the direction of deep learning or AI hardware? What could happen in terms of the kinds of algorithms, the kinds of applications that would require significant reassessment of what is on the roadmap for AI silicon? What are the things that could really say, oh, we've now got to go do something really rather different, okay, either because the kinds of algorithms that people now want are different, or because of other innovations that disrupt the current momentum? Any ideas about what the unpredictable is?
Yeah. Okay, I can try one. First of all, it's as someone said, that it's really hard to make predictions, especially about the future.
Yeah.
So that's where we are now. There can be multiple disruptions, and one of them that you can see here and there, people talking about, like quantum computing, which is once quantum computer becomes a reality, then there will be, we'll be able to solve a new range of problems. By the way, I wouldn't call it a swarm event. It's actually, black swan. It's actually great things. It's always new things and new opportunities that we can take advantage of. Yeah. And it's always great to see such a change. But there is definitely can be things And just as a quantum computer as an example, that once it's available, it can accelerate the data processing today and solve the problems that are sort of unsolvable now.
Yeah, I can definitely speak to this. So, and this may, and this is directly related to actually work that we're doing at Rain. And so, we were founded on the idea of trying to scale up analog arrays, but just over the last year, we've been working a lot with Yoshua Bengio, so one of the godfathers of deep learning, to try to uncover a way to build a fully analog neural network. And this is something that has not really been feasible for a number of reasons. But this idea of moving away entirely from a digital platform to have a fully analog, fully physical neural network, not only it would have implications to not just be very efficient and to enable it to scale and learn quickly, but also if you can understand it as a physical system, an electrical system, then you can use tools of physics to study it and ask questions and understand it. And ultimately, we can tie that back, hopefully, to the brain. So this is kind of what our North Star is at Rain, this idea of moving into the analog domain, because it is, again, fundamentally inspired by the brain propagating analog electrical signals. But I think that if that can be proven, whether it's by us or someone else, then that would be a major disruptor.
Okay. Any other thoughts on that?
Well, if you want to be really wild, we could think about some, breakthroughs in material science. CMOS has been around for a long time. We get to some, new transistor structures. We have breakthroughs, and we could lead to breakthroughs in, the whole memory architecture, the packing, gazillion number of gates, as well as improving the power efficiency. Because I think power is a big factor in all of these. Really, to get to the processing power of the human brain, as I mentioned, we are, a million times behind that. So, a single breakthrough in any of those areas, along with the algorithms, I think algorithm is a very big part of it, could really lead to 1,000x or a 1,000,000x improvement in the overall throughput, compute efficiency, power efficiency, which could lead to a whole new set of applications that are not solvable today.
Got it. So I'd love it if each of you would be so bold as to make one prediction of your own about where deep learning silicon is going. Give us some idea, maybe a little controversial idea of what you think is out there ahead of us that we should look forward to. Who wants to jump on that?
Yeah. So I'm sure yeah. So I think in terms of predictions, and again, like Michael said, it's like it's what I would say is I think there are going to be very measured and incremental steps, right, and then there are going to be revolutionary steps, right. I think the one thing we can all agree upon is that there is a lot of need for innovation in this space, right? The question is that innovation at what is the risk, right? So my prediction is that I think if somebody showed me a paper where there were the number of papers being published in this space, the number of silicon startups in the space, and the amount of investment that's going into the space, right, is huge, right? Not just in the United States, right? It's perhaps even higher in other geographies, right? So there's a lot of investment in this space. So my prediction is that I think over the next few years, what we will find is that there's going to be a consolidation, right? We will find that, well, now it's basically money chasing after a promise. There's going to be some realization that perhaps not all, that maybe silicon isn't in the solution, right? So my prediction is that what you will find is that the innovation is going to happen slightly at the higher level, meaning more in terms of coming up with certain architectures specific to certain segments, and then there'll be need for an adaptable piece of silicon where you can actually apply your innovation rather than doing it necessarily at the silicon level. Now, having said that, there will be certain segments, right, where you will need a lot more efficient silicon, right? And so that's where things like analog neuromorphic computing, either using memristors or flash technologies, right? that's going to be interesting. The question is that, where is the broader market going to be headed? And I think the broader market is perhaps going to go in more of an evolutionary step. And part of the reason really is that, backward compatibility becomes a problem, right? And so, somebody mentioned the whole solution stack. Coming up with revolutionary pieces of silicon is all great, right? But then the amount of time it takes to get the solution there, right, that can actually utilize that piece of silicon is actually, it's a huge, huge amount of effort. So I predict that, there will definitely be these revolutionary, but I think those revolutionary architectures will start to subside, and I think there'll be more of an incremental and well thought through march forward.
Yeah. Gordon, any quick thought?
Yeah. Definitely. So, one thing that I think is that most of the innovations that we've seen today, really in the last 20 years, in particular the last 10 years with respect to artificial intelligence, they have been through a conventional engineering paradigm where we have material science at the bottom, people building the next transistor, and they hand that over with few requirements to the architecture people, building the next CPU, the next GPU. And these are siloed from each other mostly. And then there are the people building the algorithms, like backpropagation, on the far end. And we've been able to get to where we are today with these three disciplines relatively divided and siloed from each other. But my belief is that the greatest innovations, the greatest pieces of impact that we'll find in the next 10 years will not be in that way of engineering. It'll be by breaking down those barriers and actually combining and asking questions that intersect between material science and device physics and, say, algorithms. For instance, how can we build an algorithm that utilizes the fundamental nonlinearity and stochasticity of a memristor in order to learn on its own in the way a Hopfield network was theorized to do some decades ago? These are the types of innovations that I think will be the most impactful and bring forward these step changes, in possibility.
Yeah. Manoj, any quick prediction?
Well, given the time, I think my view is there's so much VC money already invested into the startups on the silicon side. At least for the short term, it's going to be all evolutionary, and people are just going to keep improving on all the different vectors we talked about, whether compute efficiency, memory efficiency, and things like that. And then 5 years, 7 years down the line, more fundamental research. And that might lead to a significant breakthrough that could, completely change the paradigm.
Great. And Michael, the last word.
My take is that there's going to be some morphing of memory and the computing. It's either computational memory or memorizable computing. But the way it is distinct today, the ALU from addressable memory is very superficial. And I think the way to morph it together and have memory which is addressable by context and not by address, this is where it should go.
Well, great. Thank you all very much for those thoughts, and thank you for your participation in this panel. It's been a pleasure and an honor to get your thoughts. Lalit?
Yeah. So Chris, thanks again for being the moderator. I really, really enjoyed this session. Hopefully it was very valuable to the audience at large. I think the main purpose of having this hardware-focused panel was to inform the AI practitioners about what really happens under the hood and what really enabled this whole leap in AI in general. And again, thanks, Chris. And I want to, again, thanks the panelists, Michael Kagan, Gaurav Singh, Manoj Gujral, and Gordon Wilson. It was really a pleasure listening to all of you guys. And so the next thing is next event on September 2nd and 3rd is we have TiEcon. We have more AI ML tracks, as well as we have some great keynote speakers as seen on the screen. So this is for the audience, and again, for the panelists, if you're interested, you can also join that session. So yeah, that's it. Thanks, everyone.
Thank you very much.
Thank you. Thanks.
Stay safe.
Bye.